In this table, that's actually table 3 from page 51 in your text, you can correlate what we learned in our 2 motion activities. That would be the graph matching and the moving man. You can correlate the things that we saw there with motion about velocity and acceleration. So you can see that we have one column that looks at the initial velocity, what's happening with that, another that looks at the acceleration, and then the last column describes the motion. This should agree with the graphs that you have done on your graph matching and on your moving man simulation. One important thing that makes this easy to remember is that if the change in velocity is negative, then acceleration is also going to be negative. It's very, very helpful. If initial velocity is positive, then acceleration will be positive, and exactly the converse. If initial velocity is negative, then acceleration will be negative as well. In both cases, whatever you have is speeding up. A couple of other things you noticed from the lab and from the simulations that we did. Acceleration has direction and magnitude. So acceleration, again, is a vector quantity. Okay. Both the shape and the slope of a graph will describe the object's motion. And here would be an example. If the object is moving to the right, you have a positive displacement and a positive velocity. As that object would pick up speed, the velocity will increase in magnitude, and VF will be greater than VI. Delta V is positive. And since that velocity is positive, the acceleration is also positive. As that object would slow down, the velocity is still positive, but VF is less than VI. Okay, or VI is greater than VF. So delta V is negative. Acceleration will also be negative. And here's another little chart that will help you remind that. As speed is increasing, the slope is positive and acceleration is positive. If speed is constant, slope is 0 and acceleration is 0. And if speed is decreasing, slope is negative, acceleration would be negative as well. Now, if we want to look at motion with constant acceleration, which is our next job, we can look at this ball that's falling, and you'd find this on page 51 of your text if you want to look at it there. The ball, when it's first dropped at the top, starts out falling very, very slowly and falls at a faster rate over time until it kind of levels off at what we call a terminal velocity. Okay. The ball's velocity thus increases over time. The ball travels a greater distance over each time interval. The velocity increases by the same amount over each interval. Acceleration is constant, and the displacement of the ball increases over each of those intervals. And we know, and you'll see this again over and over again in this course, that acceleration in a downward motion is the acceleration due to gravity. It has a value of 9.81 meters per second squared on average here on Earth. And you can see that that would be what's happening here if this picture were to scale and you looked at tenth of a second intervals. Okay. Here's a graph of velocity versus time that we can look at here. And on this graph, we have marked the initial velocity of 0. We've marked the average velocity, and we've marked the final velocity as well. You'll remember that V average equals delta x over delta t, or change in displacement over change in time. If the acceleration is constant, then we can say that V average is VI plus VF divided by 2, or the average velocity is the initial velocity plus the final velocity over 2, if you need this in words. This is an equation that you should already have put on a formula card to use. This is another one that you will want to add right here. Okay, so we have displacement over change in time equaling V average equaling VI plus VF over 2, or displacement over the time interval equals initial velocity plus final velocity over 2, or delta x over delta t equals vi plus vf over 2. If we multiply both sides of this equation by delta t, which we've done right here, okay, and then simplify, we get delta x equals 1/2, because of the 2, times initial plus final velocity as a quantity, times delta t. This is how you will find displacement, or delta x, when an object is moving with constant velocity, and you know its final and initial velocities. So here, you have to know the time interval, you have to know the initial velocity and the final velocity, and you can find delta x. When you're solving these problems, remember that you want to list the given variables in a nice, neat little list with their units. You want to write the equation that describes the relationship, and you want to rearrange the equation to solve for the unknown. So the unknown should be on one side of the equal sign all by itself. You shouldn't be plugging in numbers and then rearranging. Rearrange first. Once you've done that, you can put the numbers in the equation, all of your givens. Along with units. Remember, if the units don't cancel, then you may have written your equation incorrectly or used incorrect units. It's kind of a red flag for you to go back and rethink what you may have done. Next thing you do is you do the math. Watch order of operations. Which means use the parentheses on your calculator when needed. Cancel units. And then you will write and recheck, make sure the units agree, your calculated value for reasonableness and to make sure the units worked out correctly. Is it reasonable? Did the units work out? You wanted the units to cancel to give you the unit that you hoped for in your answer.